Interfacing liquid chromatography with mass spectrometry has historically been a challenge because of the incompatibility of LC solvents with the vacuum system. Standard electron impact ionization, or EI techniques such as thermobeam, require samples to be vaporized under high vacuum for ion formation to occur. Waters' platform LCZ, LC, and ZMD mass spectrometers use a gentler technique called atmospheric pressure ionization, or API. API takes advantage of the fact that ions can form in the liquid phase or in the gaseous phase at atmospheric pressure. The LCZ, LC, and ZMD instruments offer the user two API techniques: atmospheric pressure chemical ionization, or APCI, and electrospray, or ESI, to analyze a wide variety of molecular species. While electron impact ionization is useful only with samples that can be volatilized, large molecules such as proteins that do not volatilize can be successfully analyzed by API techniques. Another major advantage of API is the type of information obtained. A common goal for mass spectrometry in general is to obtain specific structural information about a molecule, leading to unambiguous identification. If unknown compound identification is the goal, the fragmentation spectra produced by EI provide peak identification. If, however, molecular weight information is the goal of analysis for known compound conformation, then API techniques will generate protonated, deprotonated, or reducted molecules for molecular weight determination. Although the mechanism for doing so is different for APCI and ESI, both produce essentially the same type of molecular ions. Both techniques are necessary because each handles different sizes and polarities of compounds. APCI is typically used for small organic molecules up to approximately 1,500 Daltons, while ESI is very popular in the biopolymer market for proteins and peptides up to 150,000 Daltons. Samples can be analyzed with APCI using flow rates of up to 2 milliliters per minute, where ESI is more efficient at lower flow rates, in the range of 5 microliters to 1 milliliter per minute. Let's take a closer look at how sample molecules are ionized, beginning with APCI. Atmospheric pressure chemical ionization is a soft ionization technique that produces singly charged protonated or deprotonated molecules for a broad range of analytes. Sample molecules are introduced into the source through a non-metallic capillary, usually deactivated fused silica. Contained in this flow are both sample and solvent molecules. Flowing concentrically around the capillary is nebulizing gas, which creates a spray of liquid exiting from the capillary. The gas literally shears droplets off as the liquid flows out the end of the capillary. Surrounding the end of the capillary is a heater, which aids in desolvation, resulting in a hot vapor. Ionization is achieved by the application of a voltage in the range of 3 to 5 kilovolts to a metal discharge needle that lies close to the end of the probe tip. The vaporized discharge produced by this high voltage causes solvent molecules eluting into the source to be ionized into a reactive gas plasma. A combination of collisions and charge transfer reactions within this reactive plasma result in the ionization of sample molecules. In the positive ion mode, reagent ions formed from the solvent can transfer protons to the analyte, resulting in protonated molecular ions. Similar interactions occur in the negative ion mode, resulting in the formation of deprotonated molecular ions. Although electrospray, or ESI, has many similarities to APCI, the two techniques differ in the way that ions are generated. While APCI utilizes ion molecule reactions within the gas phase, electrospray ions are made in solution before the mobile phase carrying these ions reaches the mass spectrometer. Sample ions are generally formed by the gain or loss of a proton. In some cases, however, sample ions can interact with solvent molecules in solution to create adduct ions. Therefore, the solution chemistry of the mobile phase is very important. Ionized sample molecules in solution are introduced into the API source through a metal capillary. Contained in this flow are solvent and ionized sample molecules. As in APCI, nebulizing gas is flowing concentrically around the capillary and the metal probe tip, which shears droplets off as the liquid flows out the end of the capillary. A high voltage, typically between 3 and 5 kilovolts, is applied to the stainless steel capillary. The strong electric field generated by this potential, combined with nebulizing gas, produces a fine spray of charged droplets exiting from the end of the capillary. Ions are separated from the solvent by a process referred to as ion evaporation. As the droplet evaporates, the charges within the droplet get closer and closer together. Eventually, the droplet explodes into ever smaller droplets. As the droplet size is reduced, sample ions evaporate from the surface. A flow of warm nitrogen drying gas through the source helps in the evaporation process and removal of solvent. Since there is no heat applied to the capillary in ESI, this technique is useful for analysis of heat-labile sample compounds. Polar compounds of low molecular weight will generally form singly charged ions by the loss or gain of a proton. High-mass biopolymers, such as proteins and peptides, pick up more than one proton and become multiply charged ions. This feature of ESI effectively extends the mass range of the mass spectrometer being utilized. For example, since a mass spectrometer analyzes ions according to their mass-to-charge ratio, each charge that a 10,000 AMU sample ion picks up would decrease the apparent mass at which that ion would appear. The addition of 10 charges would enable that ion to be seen by a 1600 AMU quadrupole. Once ions have been formed in the atmospheric space inside the ion source, they must be directed into the mass spectrometer. The method for doing this differs between the LCZ and LC instruments. Platform LCZ and ZMD transport ions into the mass spectrometer by a dual orthogonal Z sampling technique referred to as Z-spray. The spray exiting from the end of the capillary is directed towards a baffle plate where involatiles collect. At the same time, ions are electrostatically bent 90 degrees, forcing them through the sample cone orifice and into an area of moderate vacuum within the ion block. Ions are then electrostatically bent 90 degrees a second time by an extraction cone and directed into the mass spectrometer. Most involatiles that may get into the ion block are pumped away by the rotary vacuum pump. Because of this buffer of a moderate vacuum region within the ion block, the sample cone orifice is about twice the size of the normal orifice. This allows more ions to pass through, thus greatly increasing sensitivity, while the dual orthogonal spray ensures high tolerance to buffers and complex sample matrices. In the platform LC, the capillary sprays directly onto the counter electrode, commonly referred to as a pepper pot, due to its shape and the fact that it has 4 holes symmetrically around the center. There are 4 channels through the pepper pot, each with a 60-degree followed by a 45-degree bend. This indirect ion path prevents solvent clusters and neutrals contained in the spray from passing through the sample cone and entering the mass spectrometer. This is a very sensitive interface that allows most ions through, but it is also very intolerant to involatiles like phosphate buffers that collect and block the holes in the pepper pot. For this reason, a cross-flow counter electrode is also available for use with mobile phases that contain involatile additives. The cross-flow counter electrode provides a more tortuous path for ions. The spray is directed towards a well. The ion path is bent through a channel by a combination of gas flow and electrostatic forces, and then bent a second time 90 degrees through electrostatic repulsion into the sample cone. This provides two places for involatiles to collect, thus resulting in high tolerance to additives, but also a lower sensitivity because some ions are lost. In addition to the flow of nebulizing gas around the capillary that is pushing ions in that direction, ions are pulled toward the mass spectrometer by two major forces: the vacuum within the mass spectrometer and electrostatic charges. Ions pass from the atmospheric pressure inside the source, through a moderate vacuum region beyond the sample cone, and into the high vacuum region which houses the mass analyzer. Two turbo pumps maintain the vacuum in these areas. The larger source turbo serves to pump away any spray and water clusters that get into the first high vacuum area. The smaller analyzer turbo maintains the vacuum in the quadrupole compartment. A potential is applied to the LCZ and ZMD extraction cone, which has the effect of pulling the ions into the mass spectrometer. A set of skimmer lenses accomplish the same effect in the LC instrument. The API source can be tuned to induce fragmentation of ions by a technique referred to as collision-induced dissociation, or CID. This can provide valuable structural information for low molecular weight analytes. Ion fragmentation is achieved by increasing the voltage on the sample cone. Thus, it's also referred to as cone voltage fragmentation. At normal sample cone voltage settings, ions traveling through the moderate vacuum region bump gently into other molecules in that region. Increasing the cone voltage increases the speed at which ions travel. This results in a potential difference between it and the next stage of the ion optics. The faster the ions travel, the greater the energy transfer upon impact with other molecules, and the more fragment ions are produced. Once inside the high vacuum region, ions pass first through the RF lens, or hexapole, which provides a transition from the moderate vacuum region in the source into the high vacuum region of the quadrupole mass filter. The hexapole has an RF-only voltage applied, which means that it transmits ions of all masses and takes no part in the mass filtration of ions. From the hexapole, ions pass into the pre-filter, which prevents contamination of the quadrupole mass filter. It also decouples the source from the mass filter so that the electric fields generated in the source do not influence the performance of the quadrupole mass filter. The quadrupole mass filter range varies from 1600 AMU in the LC to 4000 AMU in the LCZ instrument and 2000 or 4000 AMU in the ZMD, depending on the configuration. The quadrupole is comprised of two pairs of precisely parallel rods with electrical connections between them. A positive DC voltage is applied to two opposite rods. A negative DC voltage is applied to the alternate two rods. The DC voltage, as well as a radio frequency component, is varied to steer ions through the quad. The amplitude of this electric field determines which specific mass-to-charge ratio ions reach the detector. Only one mass-to-charge ratio ion is detected at a given time. Ions that are not selected oscillate further and further from the center, strike the rods, or are pumped away by the vacuum system. Quadrupole voltages can be set to acquire a full scan mass spectrum or to look at a single ion species. Positioned at the rear of the instrument, after the quadrupole mass filter, is the photomultiplier ion detector. Ions exiting the quadrupole are converted to electrons by a conversion diode. These electrons strike a phosphor which, when excited, emit photons. The photons strike a photocathode at the front of the photomultiplier to produce electrons, and the signal is amplified by the photomultiplier. The photomultiplier is sealed in glass and held under vacuum. This prevents contamination and allows the detector to maintain its performance for a considerably longer period than conventional electron multipliers. The signal from the photomultiplier is sent to the computer. Data acquisition and analysis is controlled by Waters MassLink software, the world-renowned data product for chromatography mass spec data handling. In addition to full scan and single ion recording acquisition modes, MassLinks also allows rapid ion polarity switching across a single chromatographic peak. This permits the acquisition of both positive and negative ions within a single run. Now, let's briefly review the steps involved in ionizing and detecting sample molecules using the API techniques we've just discussed. In APCI, sample molecules in solution enter the source as a spray of liquid created by nebulizing gas flowing around the capillary. The spray is converted to a hot vapor by a heater surrounding the capillary. Solvent molecules are ionized after coming into contact with discharge from high voltage applied to the discharge needle. A combination of collisions and charge within this area of reagent gas plasma result in the ionization of sample molecules to form protonated or deprotonated molecular ions. In ESI, ions are made in solution before the mobile phase carrying these ions reaches the mass spectrometer. Ionized sample molecules in solution enter the source as a fine spray created by a combination of nebulizing gas flowing around the capillary and a high voltage applied to the capillary. As the droplet size is reduced through evaporation, charges get closer together, resulting in an explosion of the droplets, eventually leaving individual sample ions. Sample ions pass through the sample cone, RF filter or hexapole, and pre-filter before entering the quadrupole mass filter, which separates them according to their mass-to-charge ratio. Ions are detected by the photomultiplier detector that converts ions first into electrons, then into photons for amplification by the photomultiplier. Data analysis and acquisition is controlled by MassLink software, which allows rapid ion polarity switching for analysis of both positive and negative ions in a single run. Although the mechanism for ionization differs, both APCI and ESI produce the same type of molecular ions useful for confirmation of known compounds. APCI operates at flow rates from 0.2 to 2.0 milliliters per minute, where ESI is more efficient at flow rates as low as 5 microliters per minute. While APCI is suitable for small organic molecules, ESI is popular for larger molecules such as proteins and peptides that cannot be analyzed with electron impact ionization techniques. No matter what the nature of your research, APCI and ESI mass spectral detection can speed you on the way to results that you couldn't get with a UV detector.